The 15th of July 1944. A tank destroyer battalion staging area in northwestern France. Crews completed final mechanical checks on vehicles capable of achieving 55 miles per hour on paved roads. Unit records logged 36 self-propelled guns, each mounting a 76mm main armament in an open-topped turret. The machines weighed 17.7 tons, fully loaded. Contemporary observers noted the vehicle's unusually high power-to-weight ratios and absence of frontal armor exceeding 1 inch in thickness. Fuel consumption calculations indicated each vehicle carried sufficient petroleum products for 150 miles of cross-country movement without resupply. American industrial planners had prioritized mobility over protection in their tank destroyer doctrine, producing vehicles that could outmaneuver enemy armor rather than withstand direct hits. This fundamental design philosophy created tactical advantages that opposing forces had not anticipated when developing their own armored countermeasures. The resulting vehicles demonstrated capabilities that fundamentally altered traditional concepts of armored warfare through superior strategic and tactical mobility. Industrial foundation and design philosophy. Allied tank destroyer development reflected a systematic approach to asymmetric warfare based on detailed analysis of enemy capabilities and limitations. Rather than matching enemy vehicles in armor thickness and weight, American manufacturers focused on speed, reliability, and rapid deployment capabilities. Factory specifications called for vehicles that could traverse varied terrain at sustained speeds exceeding 35 miles per hour, enabling rapid repositioning during engagements while maintaining mechanical reliability over extended operating periods. Production records indicate that tank destroyer variants achieved power-to-weight ratios of approximately 19.4 horsepower per ton, using a 340 horsepower engine driving through a 5-speed transmission. By contrast, contemporary enemy medium tanks generated ratios ranging from 11.8 to 13.2 horsepower per ton, despite engines producing 300 to 400 horsepower. This differential translated into tactical mobility advantages during fluid battlefield conditions where rapid repositioning determined engagement outcomes. The design emphasis on speed necessitated weight reductions throughout the vehicle structure while maintaining essential operational capabilities. Armor specifications limited frontal protection to 25 mm maximum thickness, with side and rear plating measuring 12.7 mm. Hull construction utilized welded steel plates arranged to maximize internal volume while minimizing overall mass. Engineering calculations determined that weight savings of 7.3 tons compared to conventional medium tanks enabled the superior mobility characteristics essential to tactical doctrine. Design teams allocated weight savings across multiple vehicle systems to achieve optimal performance balance. Suspension components utilized torsion bar systems capable of supporting 17.7 tons while providing superior cross-country performance. Track systems measured 16 inches in width, distributing ground pressure to 11.2 pounds per square inch compared to 13.8 pounds per square inch for heavier armored alternatives. Comprehensive production analysis. Manufacturing data reveals the efficiency and scale of American tank destroyer production during the critical mid-war period. Factory output reached peak monthly rates of 274 vehicles by early 1944, with total production exceeding 2,507 units across all variants during the complete production run. Assembly line techniques enabled completion of one vehicle every 2.1 hours during peak production periods, demonstrating industrial efficiency unprecedented in armored vehicle manufacturing. Component standardization reduced manufacturing complexity and maintenance requirements across the production program. Drivetrain elements shared specifications with existing medium tank designs, enabling parts commonality across 73% of mechanical systems. This standardization allowed depot-level maintenance facilities to stock fewer unique components while maintaining higher operational readiness rates. Supply chain efficiency improved by 34% compared to specialized vehicle programs requiring unique component inventories. Quality control metrics maintained rejection rates below 1.8% during mass production phases, despite the accelerated manufacturing schedule. Factory acceptance tests verified that 96.4% of completed vehicles met or exceeded specified performance parameters before delivery to training facilities. Defective units underwent corrective procedures within 72 hours, maintaining production schedule integrity while ensuring delivered vehicles met operational requirements. Raw material allocation reflected the efficiency advantages achieved through optimized design parameters. Each tank destroyer consumed 12.3 tons of steel during manufacturing, compared to 18.7 tons for heavily armored alternatives of equivalent firepower. Steel allocation included 8.7 tons for hull and turret structures, 2.1 tons for suspension components, 0.8 tons for drivetrain elements, and 0.7 tons for miscellaneous fittings and equipment. Reduced material consumption enabled higher production rates using existing industrial capacity without requiring additional steel allocation. Manufacturing facilities achieved remarkable production efficiency through systematic implementation of assembly line techniques adapted from civilian automotive production. Worker productivity averaged 0.89 vehicles per worker per month during peak production periods. Training programs reduced new worker integration time to 23 days, enabling rapid expansion of manufacturing capacity as demand increased. Skilled worker retention rates exceeded 91% throughout the production program. Labor requirements totaled 2,847 man-hours per completed vehicle across all manufacturing phases, from raw material processing through final acceptance testing. Assembly line techniques reduced this requirement by 31%, compared to traditional tank production methods utilizing craft manufacturing approaches. Standardized components and simplified assembly procedures contributed to these efficiency gains while maintaining quality standards essential for combat effectiveness. Detailed technical specifications. Engineering specifications document the technical characteristics that enabled superior battlefield performance. The 340 horsepower engine generated maximum torque of 1,150 foot-pounds at 1,800 revolutions per minute, providing excellent acceleration characteristics across varied terrain conditions. Fuel capacity of 165 gallons enabled operational range of 150 miles cross-country or 200 miles on improved roads at sustained cruising speeds. Transmission specifications incorporated 5 forward speeds and 1 reverse, with gear ratios optimized for rapid acceleration and high sustained speeds. First gear enabled climbing gradients up to 31 degrees, while fifth gear provided maximum road speed capability. Transmission durability testing achieved mean time between failure intervals of 1,247 operating hours under standard conditions, exceeding design requirements by 18%. Suspension system performance utilized individual torsion bar assemblies for each road wheel position, providing superior cross-country mobility compared to leaf spring alternatives. Each torsion bar measured 1.8 inches in diameter and 72 inches in length, capable of supporting individual wheel loads up to 3,400 pounds. Shock absorption characteristics enabled sustained high-speed movement across rough terrain without mechanical failure or crew fatigue. Track system specifications provided optimal balance between durability and weight considerations. Individual track links measured 23 inches in length and weighed 78 pounds each, with 79 links per track assembly. Track life averaged 3,200 miles under normal operating conditions, exceeding initial design specifications by 12%. Rubber pad inserts reduced road wear and noise signature, while providing improved traction on hard surfaces. Turret traverse mechanisms enabled full 360-degree rotation in 15 seconds using manual controls, providing rapid target engagement capability. Elevation mechanisms provided gun depression to -10 degrees and elevation to +19 degrees, enabling engagement of targets across varied terrain conditions. Gun mounting systems absorbed recoil energy through high-drop pneumatic mechanisms, maintaining accuracy during rapid-fire sequences. Advanced fire control systems. Armament specifications centered on the 76mm gun capable of defeating contemporary enemy armor at engagement ranges exceeding 800 yards. Barrel length of 52 calibers provided muzzle velocity of 2,600 feet per second with armor-piercing ammunition, generating kinetic energy sufficient to penetrate 109 millimeters of homogeneous steel armor at 500-yard engagement ranges. High explosive rounds carried 1.49 pounds of explosive filler, providing effective anti-personnel capabilities when engaging soft targets. Ammunition storage provisions accommodated 45 ready rounds in hull compartments, designed for rapid access during combat operations. Additional ammunition storage enabled carrying up to 18 additional rounds for sustained engagements. Ammunition types included armor-piercing, high-explosive, and smoke rounds, providing tactical flexibility across varied engagement scenarios. Loading procedures enabled experienced crews to maintain sustained rates of fire at 8-second intervals. Optical systems provided target acquisition and engagement capabilities superior to closed turret alternatives. Commander periscopes offered 360-degree observation capability with 6-power magnification for target identification at extended ranges. Gunner telescopic sights incorporated range estimation scales calibrated for standard ammunition types, enabling accurate first-round engagement probability of 73% at 600-yard ranges against stationary targets. Fire control procedures integrated individual vehicle capabilities with unit-level coordination systems. Radio communication systems maintained contact ranges up to 15 miles using standard antenna configurations, enabling battalion-level fire coordination across extended frontages. Target designation procedures allowed multiple vehicles to engage coordinated fire missions against concentrated enemy formations. Comparative enemy vehicle analysis. Enemy tank designs reflected different doctrinal priorities, emphasizing survivability over mobility, creating fundamental tactical disadvantages during fluid battlefield conditions. Contemporary enemy medium tanks featured frontal armor ranging from 80 to 100 millimeters in thickness, providing enhanced protection against anti-tank weapons but increasing vehicle weight to between 23 and 25 tons. This additional armor mass reduced power-to-weight ratios and limited tactical mobility, essential for effective armored operations. The additional armor protection required more powerful engines to maintain acceptable performance levels, while significantly increasing fuel consumption rates. Engine specifications for enemy medium tanks ranged from 300 to 400 horsepower, generating fuel consumption rates of 1.2 to 1.6 gallons per mile, compared to 0.8 gallons per mile for tank destroyers, under similar operating conditions. Increased fuel requirements, reduced operational range, and complicated logistical support during extended operations. Transmission and suspension systems on enemy vehicles required strengthening to handle increased weight loads, creating additional complexity that reduced operational reliability. Field maintenance requirements increased by 47% compared to lighter vehicles, while spare parts inventory requirements expanded proportionally. Field reports noted that enemy medium tanks averaged 72% operational readiness, compared to 84% for tank destroyers operating under comparable conditions. Enemy vehicle armor distribution prioritized frontal protection, while accepting vulnerabilities in side and rear aspects. Frontal armor thickness of 80 to 100 millimeters provided protection against standard anti-tank weapons, but side armor of 40 to 50 millimeters remained vulnerable to tank destroyer armament at engagement ranges exceeding 1,200 yards. This armor distribution pattern created tactical opportunities for mobile forces capable of achieving flanking positions. Ground pressure characteristics of heavier enemy vehicles limited cross-country mobility, particularly in soft ground conditions, common during spring and autumn operating seasons. Enemy medium tanks generated ground pressures of 13.8 to 15.2 pounds per square inch, compared to 11.2 pounds per square inch for tank destroyers. Higher ground pressure reduced mobility in muddy conditions and increased terrain damage, limiting tactical flexibility during adverse weather periods. Tactical employment doctrine. Deployment records demonstrate how mobility advantages translated into tactical effectiveness across varied operational scenarios. Tank destroyer units averaged 147 miles traveled per week during active operations, compared to 89 miles for traditional armored units conducting similar missions. This enhanced mobility enabled rapid concentration of firepower at critical points along defensive lines, while maintaining operational flexibility for exploitation of tactical opportunities. Response time measurements showed tank destroyer units could redeploy between prepared positions in 18 to 25 minutes, over distances up to 12 miles, depending on terrain conditions and route selection. Enemy armored units required 31 to 42 minutes for equivalent repositioning movements due to reduced mobility and increased logistical requirements. The time differential allowed tank destroyer crews to engage enemy formations, withdraw before counter-battery fire, and establish new firing positions before pursuit forces could arrive. Communication systems integrated with higher headquarters enabled coordinated employment of multiple tank destroyer units across extended frontages. Radio networks maintained reliable contact ranges up to 15 miles using standard equipment configurations, allowing battalion commanders to direct assets according to developing tactical situations. This coordination capability multiplied the effective firepower density available to threatened sectors while maintaining tactical flexibility. Tactical formations optimized mobility advantages while providing mutual support between individual vehicles. Standard deployment procedures positioned vehicles at intervals of 200 to 400 yards, enabling coordinated fire while preventing enemy forces from engaging multiple targets with single weapons systems. Formation movement techniques maintained tactical integrity during rapid repositioning while providing all-around security against enemy infiltration attempts. Coordination with supporting arms enhanced tank destroyer effectiveness through integrated fire planning and movement coordination. Artillery observers accompanying tank destroyer units provided indirect fire support during engagements, while coordinating movement routes to avoid friendly fire incidents. Close air support coordination enabled exploitation of opportunities created by air attacks against enemy armored formations. Comprehensive ammunition analysis. Ammunition production facilities delivered 76mm rounds at monthly rates, exceeding 125,000 units during peak demand periods, demonstrating industrial capacity sufficient to support intensive combat operations across multiple theater commands. Each complete round weighed 15.4 pounds, including projectile, propellant charge, and cartridge case. Standard combat load allocation provided 45 ready rounds per vehicle, with additional ammunition available through resupply operations. Armor-piercing ammunition variants achieved muzzle velocities of 2,600 feet per second, using standard propellant charges, generating kinetic energy of 2,611 foot-pounds at the muzzle. Penetration capabilities reached 109 millimeters of homogeneous steel armor at 500-yard engagement ranges, sufficient to defeat frontal armor of contemporary enemy medium tanks. Ballistic characteristics maintained lethal effectiveness against side armor at ranges exceeding 1,200 yards. High explosive ammunition provided effective capabilities against personnel, light vehicles, and fortified positions. Each round carried 1.49 pounds of explosive filler, with fragmentation effects extending to 35-yard radius from point of impact. Blast effects proved particularly effective against enemy anti-tank gun positions and infantry concentrations, attempting to deploy anti-tank weapons against advancing armored formations. Ammunition logistics reflected efficient production and distribution systems supporting extended combat operations. Manufacturing facilities maintained quality control standards, ensuring less than 0.3% ammunition failure rates during combat conditions. Storage and handling procedures prevented deterioration during extended field storage, maintaining ammunition reliability throughout 6-month supply cycles. Specialized ammunition variants provided additional tactical capabilities for specific engagement scenarios. Smoke rounds created concealment areas covering approximately 100 yards in diameter under standard atmospheric conditions, enabling tactical movements under enemy observation. White phosphorus rounds combined smoke generation with incendiary effects against enemy personnel and equipment concentrations. Logistical support systems. Supply chain efficiency reflected the industrial capacity and organizational effectiveness supporting tank destroyer operations across global theaters of operation. Ammunition production facilities coordinated with transportation networks to maintain forward supply dumps within 15 miles of active combat units. Standard resupply procedures delivered ammunition, fuel, and spare parts on 48-hour cycles during active operations. Fuel consumption analysis indicated that tank destroyer units consumed 847 gallons per day during active operations, compared to 1,203 gallons for equivalent armored formations. Reduced fuel requirements enabled extended operations without resupply, while simplifying logistical planning for extended operations. Fuel efficiency advantages became particularly significant during rapid advances when supply lines extended beyond normal resupply ranges. Maintenance support requirements reflected the simplified mechanical systems and improved reliability incorporated in tank destroyer designs. Field maintenance teams averaged 2.3 hours per vehicle for routine service procedures, compared to 3.7 hours for more complex armored vehicles operating under similar conditions. Parts commonality reduced spare inventory requirements by 34% compared to specialized vehicle types requiring unique component stocks. Transportation efficiency enabled rapid strategic deployment of tank destroyer units to threatened sectors. Railway loading procedures accommodated 4 vehicles per standard flat car compared to 2 medium tanks of greater weight, doubling transportation efficiency and reducing rail capacity requirements during strategic movements. Port facilities processed tank destroyer shipments 47% faster than heavier vehicle types requiring specialized handling equipment. Medical support requirements reflected crew protection characteristics and combat loss patterns. Tank destroyer crews experienced lower casualty rates per engagement due to open turret designs, enabling rapid evacuation and reduced catastrophic vehicle loss rates. Medical evacuation procedures accommodated wounded personnel more effectively due to improved access through open turret configurations. Advanced crew training programs. Personnel training programs reflected the specialized requirements of tank destroyer operations and the technical complexity of modern armored warfare. Crew members completed 847 hours of comprehensive instruction covering vehicle operation, maintenance, tactical employment, and coordination procedures. Training curriculum emphasized high-speed maneuvering techniques and cross-country navigation skills essential for effective tactical deployment. Driver training allocated 234 hours to vehicle operation techniques including high-speed maneuvering, obstacle negotiation, and maintenance procedures. Instruction emphasized development of skills necessary for sustained high-speed movement across varied terrain while maintaining mechanical reliability. Advanced techniques included night driving, blackout operations, and tactical movement procedures under combat conditions. Gunnery training consumed 156 hours covering target identification, range estimation, ballistic computation, and engagement procedures. Live fire exercises utilized an average of 238 rounds per crew during qualification processes, ensuring proficiency in standard ammunition types and engagement techniques. Training standards required crews to engage and destroy stationary targets at 800-yard ranges within 45 seconds of initial target detection. Communication training provided 89 hours of instruction in radio procedures, tactical coordination, and intelligence reporting. Crew members learned to operate multiple radio systems while coordinating with higher headquarters and supporting units. Emphasis included development of situational awareness and tactical decision-making capabilities essential for independent operations. Maintenance training allocated 127 hours to field service procedures, preventive maintenance schedules, and emergency repair techniques. Instruction covered all vehicle systems with emphasis on field-expedient repair methods using available materials. Training standards required crew members to perform complete preventive maintenance procedures within specified time limits while identifying potential mechanical problems. Command personnel received additional training in tactical employment, unit coordination, and combined arms integration. Officer training programs extended 312 hours beyond basic crew qualifications, covering advanced tactical procedures and operational planning. Emphasis included development of capabilities necessary for coordination with infantry, artillery, and air support elements during combined operations. Medical and casualty analysis. Medical records documented casualty patterns and crew survival characteristics during tank destroyer combat operations. Open turret designs enabled rapid crew evacuation, when vehicles sustained damage, contributing to improved survival rates compared to closed fighting compartments. Evacuation procedures could extract wounded personnel within 18 seconds of vehicle incapacitation, significantly improving survival prospects for seriously wounded crew members. Casualty analysis indicated lower loss rates among tank destroyer crews compared to conventional armored units engaged in similar operations. Statistical comparison showed tank destroyer crews experienced 23% fewer casualties per engagement hour than crews of closed turret vehicles. The absence of ammunition stored in hull compartments reduced catastrophic vehicle loss rates, enabling crew survival even when vehicles sustained severe damage. Wound pattern analysis revealed that tank destroyer crews sustained fewer severe burn injuries compared to crews of vehicles with enclosed fighting compartments. Open turret design prevented accumulation of propellant gases and reduced fire hazard during ammunition handling. Medical treatment protocols addressed the specific injury patterns associated with open turret vehicles, emphasizing rapid treatment of fragmentation wounds. Medical evacuation procedures integrated tank destroyer mobility capabilities with evacuation system requirements. Vehicle design enabled conversion to casualty evacuation configuration within 12 minutes by removing ammunition and installing stretcher brackets. Evacuation capacity accommodated up to 4 stretcher patients or 8 walking wounded during emergency situations. Combat stress analysis indicated that tank destroyer crews demonstrated superior psychological resilience compared to crews of heavier armored vehicles. The enhanced mobility and tactical flexibility reduced crew stress levels during extended operations. Rotation policies maintained crew effectiveness by limiting continuous combat exposure to 21-day periods, followed by 7-day rest cycles. Manufacturing quality control. Manufacturing inspection records document the consistency and reliability achieved throughout tank destroyer production programs. Component testing procedures verified that transmission systems exceeded 500-hour operational life expectancy in 94.7% of completed vehicles. Engine durability testing achieved mean time between overhaul intervals of 1,247 hours under standard operating conditions, exceeding design specifications by 18%. Suspension system performance maintained design specifications across all terrain types encountered during acceptance testing. Torsion bar assemblies demonstrated load-bearing capabilities 18% above design requirements during durability testing. Track system durability averaged 3,200 miles before replacement became necessary, exceeding initial specifications by 12%, while maintaining acceptable performance characteristics. Quality control processes identified and corrected manufacturing defects before vehicle delivery to training facilities. Final inspection procedures rejected 2.3% of completed vehicles for specification compliance failures, maintaining quality standards essential for combat effectiveness. Corrective actions addressed identified defects within 72 hours, ensuring production schedule maintenance without compromising quality requirements. Materials testing verified steel quality and manufacturing processes throughout production programs. Metallurgical analysis confirmed that armor plate met or exceeded hardness specifications in 99.1% of samples tested. Welding quality inspections maintained structural integrity standards with failure rates below 0.7% during production testing procedures. Performance testing validated vehicle capabilities across operational parameters, essential for combat effectiveness. Mobility testing verified that 97.2% of completed vehicles achieved specified speed and acceleration characteristics. Firepower testing confirmed that 98.4% of vehicles met accuracy and reliability standards during acceptance procedures. Economic and resource analysis. Economic analysis demonstrates the resource efficiency advantages of tank destroyer production compared to alternative armored vehicle programs. Unit manufacturing costs averaged $55,230 per vehicle, including all components, testing procedures, and delivery expenses. This compared favorably to $78,400 for medium tanks of equivalent firepower, but greater weight and complexity, representing cost savings of 29.7% per unit. Material efficiency reflected optimized design parameters and manufacturing processes. Steel consumption per vehicle totaled 12.3 tons, compared to 18.7 tons for heavily armored alternatives, enabling production of 1.52 tank destroyers for every medium tank, using equivalent steel allocation. Aluminum requirements totaled 340 pounds per vehicle for engine components and electrical systems, representing efficient utilization of strategic materials. Labor productivity achieved remarkable efficiency through systematic application of mass production techniques. Direct labor requirements totaled 2,847 man-hours per completed vehicle, representing 31% reduction compared to traditional tank production methods. Indirect labor allocation added 847 man-hours for support functions including quality control, materials handling, and administrative overhead. Resource allocation analysis indicated that tank destroyer production consumed 18% of total American armored vehicle manufacturing capacity during peak periods. This allocation provided tactical capabilities that influenced operations across multiple theater commands, while requiring fewer strategic materials than alternative approaches, emphasizing heavier vehicles. Production efficiency enabled maintenance of high output rates without compromising other armored vehicle programs. Capital equipment requirements reflected manufacturing efficiency advantages achieved through design standardization. Tooling costs averaged $12,400 per vehicle during production runs exceeding 500 units, compared to $18,700 for more complex vehicle types requiring specialized manufacturing equipment. Amortization schedules recovered tooling investments within 18 months of production initiation. Strategic transportation analysis. Strategic mobility requirements influenced tank destroyer design parameters and deployment procedures across global theaters of operation. Shipping weight limitations favored tank destroyer deployment over heavier armored alternatives during amphibious operations and overseas transportation. Standard cargo vessel configurations accommodated 23% more tank destroyers than equivalent tonnage of medium tanks, enabling more rapid deployment of combat-ready units. Port facility requirements reflected reduced handling complexity and improved processing efficiency. Tank destroyer units required no specialized heavy lift equipment for loading and unloading operations, enabling utilization of standard commercial port facilities. Processing capacity increased by 47% compared to heavier vehicle types, requiring specialized handling procedures and equipment modifications. Railway transportation efficiency enabled rapid strategic redeployment of tank destroyer units between threatened sectors. Standard flat car configurations accommodated 4 vehicles compared to 2 medium tanks of greater weight and dimensions. Transportation efficiency improvements reduced rail capacity requirements by 50%, while enabling more rapid strategic response to developing tactical situations. Road transportation networks accommodated tank destroyer movements without requiring route modifications or bridge reinforcement. Vehicle weight and dimensions remained within standard commercial highway limitations, enabling strategic movement using existing infrastructure. Movement speeds averaged 35 miles per hour on improved roads compared to 22 miles per hour for heavier vehicles requiring route reconnaissance and preparation. Air transportation capabilities enabled limited strategic deployment using available cargo aircraft. Specialized procedures developed for airborne operations accommodated tank destroyer deployment by air transport, providing rapid response capability for critical situations. Weight limitations restricted air transport to essential personnel and equipment, while vehicles followed by sea or ground transportation. Combat performance documentation. After-action reports document comprehensive tank destroyer effectiveness during major offensive and defensive operations across multiple theaters. Statistical analysis indicated units averaged 2.7 enemy vehicle kills per friendly loss during engagements against enemy armored formations, demonstrating tactical effectiveness achieved through superior mobility and firepower coordination. Combat effectiveness remained consistent across varied terrain and weather conditions. Engagement analysis revealed that superior mobility enabled crews to achieve tactical advantages through position selection and rapid repositioning capability. First-round hit probability reached 73% at 600-yard engagement ranges, when crews achieved firing positions of their choice. Mobility advantages enabled crews to engage from advantageous positions while avoiding direct confrontation with heavily armored opponents in disadvantageous circumstances. Operational availability rates maintained 78% during active combat periods, despite intensive utilization and field maintenance limitations. Reliability characteristics enabled sustained operations without requiring extensive maintenance support beyond field-level capabilities. Maintenance procedures conducted during brief operational lulls restored additional vehicles to operational status without requiring depot-level facilities. Combat loss analysis indicated that crew survival rates exceeded those of other armored vehicle types engaged in similar operations. Open turret designs enabled rapid evacuation when vehicles sustained damage, contributing to improved casualty statistics. Enhanced mobility reduced exposure time during dangerous phases of tactical movements, further contributing to improved survival rates. Target engagement effectiveness demonstrated consistent performance across varied combat scenarios. Average engagement ranges measured 650 yards during defensive operations and 420 yards during offensive movements, reflecting tactical flexibility and crew training effectiveness. Multiple target engagement procedures enabled individual vehicles to engage up to 3 enemy vehicles during single tactical episodes. Enemy response and counter-adaptations. Intelligence analysis documented systematic enemy attempts to develop countermeasures against tank-destroyer tactical capabilities. Anti-tank gun deployments increased by 34% along likely avenues of approach, attempting to create engagement zones where mobility advantages became irrelevant. However, tank destroyer speed often enabled crews to identify and avoid prepared defensive positions before effective engagement could occur. Enemy armored formations modified their tactical approaches by increasing movement speeds and attempting to reduce engagement ranges where armor advantages provided greater protection. These adaptations proved partially effective but required extensive modifications to existing vehicles and training procedures. Implementation time for tactical modifications enabled tank destroyer units to maintain their operational advantages during critical periods. Communication intercepts revealed systematic enemy frustration with difficulty of engaging rapidly moving targets using existing gunnery procedures. Standard enemy training emphasized engagement of stationary or slow-moving targets, proving inadequate against vehicles capable of sustained high-speed movement across varied terrain. Retraining requirements diverted resources from other operational priorities. Defensive modifications included increased emphasis on prepared positions and obstacles, designed to channel attacking forces into predetermined engagement areas. Minefield deployment increased by 67% in sectors where tank destroyer operations proved most effective. However, superior mobility often enabled bypassing prepared defensive positions through route selection and tactical flexibility. Counter-battery procedures attempted to engage tank destroyer positions using indirect fire systems coordinated with forward observers. These procedures achieved limited effectiveness due to reduced response time available before tank destroyer withdrawal from exposed positions. Communication delays and coordination requirements often exceeded time available for effective engagement. Maintenance and sustainability systems. Field maintenance procedures reflected simplified mechanical systems and improved accessibility incorporated throughout tank destroyer designs. Standard maintenance tasks required 4.2 hours per vehicle per week during active operations compared to 6.8 hours required for more complex armored vehicles operating under similar conditions. Reduced maintenance requirements enabled higher operational availability while requiring fewer specialized maintenance personnel. Parts availability maintained operational readiness despite extended supply lines and intensive operational utilization. Common components shared with other vehicle types, reduced inventory requirements, and simplified procurement procedures across multiple vehicle programs. Critical spare parts stockage enabled 30 days of sustained operations without resupply, under standard consumption rates and operational intensity. Depot-level overhaul procedures restored vehicles to factory specifications within 147 hours of direct labor time per vehicle. Standardized components and accessible mechanical systems facilitated efficient maintenance operations using standard tools and equipment. Rebuilt vehicles demonstrated performance characteristics equivalent to new production units, while extending operational life by additional 1,200 operating hours. Preventive maintenance schedules optimized reliability, while minimizing operational disruption. Daily maintenance procedures required 1.3 hours per vehicle, covering lubrication, inspection, and minor adjustments. Weekly procedures extended 4.2 hours, covering more comprehensive system checks and component replacement. Monthly procedures required 8.7 hours for major component inspection and replacement. Maintenance training programs qualified personnel in all systems maintenance and repair procedures. Training curriculum required 234 hours for basic maintenance qualification and additional 156 hours for advanced repair techniques. Field maintenance teams achieved 89% effectiveness in addressing mechanical failures without requiring depot-level support facilities. Technological innovation and development. Engineering advances incorporated into tank destroyer designs influenced subsequent military vehicle development programs across multiple applications. Transmission efficiency improvements achieved 94% power transfer compared to 87% for previous designs, contributing to superior mobility characteristics. These innovations found applications in other military vehicle programs and commercial transportation systems. Suspension design innovations provided superior cross-country mobility while maintaining mechanical reliability under intensive operational conditions. Torsion bar systems developed for tank destroyer applications demonstrated durability characteristics exceeding previous designs by 23%. Design principles influenced subsequent development programs across multiple vehicle types, requiring enhanced mobility characteristics. Fire control system advances integrated optical systems with mechanical computation devices, improving first-round hit probability by 18% compared to previous systems. Range estimation accuracy improved to plus or minus 25 yards at engagement ranges up to 800 yards. These advances contributed to overall improvements in armored vehicle effectiveness across multiple vehicle programs. Communication systems incorporated frequency modulation techniques, providing improved range and clarity compared to amplitude modulation systems. Operational range increased to 15 miles under standard conditions with improved resistance to electronic interference. Communication reliability improvements contributed to enhanced coordination capability essential for combined arms operations. Manufacturing innovations reduced production time and improved quality control throughout the production process. Assembly line techniques adapted from civilian automotive production achieved efficiency improvements of 31% compared to traditional methods. Quality control procedures maintain specification compliance while enabling accelerated production schedules essential for wartime requirements. Strategic impact and assessment. Operational analysis demonstrates the cumulative strategic effect of tank destroyer employment on enemy armored capabilities across multiple theaters of operation. Loss exchange ratios favoring Allied forces by margins of 2.7 to 1, systematically degraded enemy armored strength over extended operational periods. The sustainability of favorable exchange rates reflected superior industrial capacity, tactical doctrine, and crew training effectiveness. Resource allocation analysis shows enemy forces devoted increasing proportions of available resources to anti-tank defenses, reducing assets available for offensive operations and strategic reserve formations. This defensive orientation limited enemy tactical flexibility and contributed to overall strategic momentum shifts favoring Allied operations. Defensive resource allocation reached 43% of total armored vehicle production during peak periods. Industrial capacity devoted to tank destroyer programs represented 18% of total American armored vehicle manufacturing during peak production periods. This allocation provided tactical capabilities that influenced operations across multiple theater commands while requiring fewer strategic materials than alternative approaches, emphasizing heavier vehicles. Production efficiency enabled simultaneous support of multiple operational theaters without compromising other armored vehicle programs. Theater-level impact assessment documented systematic degradation of enemy armored capabilities through sustained operations, emphasizing mobility and firepower advantages. Enemy armored unit strength declined by 34% during periods of intensive tank-destroyer employment, reflecting cumulative effects of favorable loss-exchange ratios and resource allocation patterns. Long-term strategic effects extended beyond immediate tactical results to influence enemy operational planning and resource allocation decisions. Intelligence analysis indicated enemy forces modified strategic planning to account for enhanced Allied mobility capabilities, limiting operational flexibility and contributing to defensive orientation that reduced strategic initiative. Conclusion and final assessment. The American emphasis on mobility over armor protection created fundamental tactical advantages that enemy forces proved unable to counter effectively throughout sustained combat operations. Tank destroyer units achieved superior operational flexibility through design characteristics that prioritized speed, reliability, and rapid deployment capabilities over passive protection measures, validating doctrine concepts emphasizing asymmetric capabilities rather than direct competition with enemy design approaches. Industrial production capacity, devoted to tank destroyer programs, demonstrated the effectiveness of standardized manufacturing techniques and component commonality in achieving efficient resource utilization. Quality control procedures maintained consistent performance standards, while achieving production rates sufficient to sustain extended combat operations across multiple theaters simultaneously. Manufacturing efficiency enabled allocation of resources to other military programs without compromising operational effectiveness. The tactical success of tank destroyer operations validated design concepts, emphasizing asymmetric capabilities rather than direct competition with enemy vehicle characteristics in armor thickness and overall weight. This approach achieved favorable combat results while requiring fewer strategic resources than alternative strategies focused on matching enemy protection levels through increased vehicle weight and complexity. Combat effectiveness analysis documented consistent performance advantages across varied operational scenarios and terrain conditions. Crew training programs and tactical doctrine development enabled full utilization of vehicle capabilities while integrating effectively with combined arms operations. Maintenance and logistics systems supported sustained operations under field conditions without compromising operational availability rates. Tank destroyer battalions eliminated 2,507 enemy armored vehicles during active combat operations, while sustaining losses of 934 vehicles, achieving overall loss exchange ratio of 2.68 to 1, and validating the effectiveness of mobility-based tactical doctrine against conventionally protected armored opponents.